Okay, so today's exercise topic is about finite impulse response design by windowing method. Okay, and where we start, I will show you the windowing method principle, and we have a system that has a sampling rate, and we designed first a low-pass filter with cutoff frequency of FC, for example, well, I'll mark some numbers on the MATLAB there. So I try first to do an ideal system, and then I will do the same thing what I did on the exercise. Do the sync and sample it and see what happens to the frequency response and that kind of things. Okay, and now I require full attention from all of you. Okay, so let's start with the simple low-pass filter, and just a curiosity. Let's take what happens if we have a simplest one, which is the average filter. Easiest low-pass filter is an average filter. So running average. And we only have one parameter to fix there, which is the length of the filter. For example, from 1 times 11 divided by 11. So this is a 11 running average filter parameters, which has the frequency response of the following. I don't care about the sampling rate yet. Okay, it looks like that. So from that one we can see, okay, we can only get about 20 dB attenuation on stop band. Oh, maybe I should actually blow it up a little bit. So that's 20 dB attenuation on stop band. Stop band starts here. Minus 3 dB point is somewhere there. Not a good filter at all, I would say. Let's try another one. Only parameters we can change here is basically just this number of points and make it 111 point running average filter. That should be somehow better. It's more averages. Yeah, somehow it is, but still we are at the maximum we have about minus 40 dB. So we just 40 dB attenuation here. Okay. And at the same time, we also kind of lost control of what the cutoff frequency would be. So we don't, in running average, we cannot control the cutoff frequency, and also the stop band attenuation is not that great. Even with 111 points, we still have 40 dB, just 40 dB attenuation. That's not much for that size filter. Okay, let's start real design. Design with sample sync. And let's put some values here, since I don't like designing with arbitrary values. For example, sampling rate of, okay, let's make it easy, 2000 samples per second. Our sampling rate, there. Then cutoff frequency, I will put just for curiosity, 100 Hertz cutoff frequency. On this one, Nyquist frequency would be 500 Hertz and cutoff frequency 100 Hertz for this example. low pass cutoff frequency. Then a sampled sink, and there we need a sampled sink with both sides of origin, so we need also negative index values, which are then just time shifted to positive. But anyways, the for example, like this, nn equals from -5 to 5. So these are sampling indexes. Then I need to take a look at my formula on here. Let's see. Build the design video. Okay. Build the design. I need that formula since I never remembered it by heart. Okay, there we go. H of n is fundamentally 2 times the cutoff frequency divided by sampling rate times sink of 2 times cutoff frequency divided multiplied by n times sampling rate. So let's just apply that one. By the way, sampling rate over 2 is also Nyquist frequency. Okay, so Nyquist frequency equals fs over 2. Maybe I can use that one. Here's Q. There. So then we sample the sign, and this is now when we sample it like that one, we are actually saying this is a box type window. Just those values and no zeros on either side. That's a box multiplication. So that was Fc over Fn times, what else? Yeah, Fc over Fn, and sink Fc over Fn times n. Okay, that's not that hard. Fc over Fn times n, index. Sample sink with box window. There. And it looks like this. Oops. Okay. That's 11 terms. It's kind of bell-shaped curve. And then we can actually take a look at what it looks like here. HS11, those are then sampling rate. Oh, right. The amplitude response or frequency response of the system looks like that. Not much different from the running average filter, except in one way. Actually, it doesn't show up that well in here, but now we can control the cutoff frequency. So now we have that 3 dB point at 100 Hertz. And seeing is believing. Let's try more points. So HH1, oops, let's make NN1 as 55, 55 sampling indexes. Okay, so now I have the same length, 111 points as I had in running average. And HH1 equals that one times that one. It's still the okay. Let's see the frequency response of this one. All right. So having that sink there, now we can control the cutoff frequency. We still have the 111 points as in my previous filter here, the HS1, which was just the running average HS1. But now we have also the, now we can control the cutoff frequency. But still, we have the box window, meaning that the rest of that filter is more or less as crappy as a running average filter, since the attenuation goes only at around that 40 dB attenuation only, not much. But that now we can apply some smoother windows. Again, let me get some help from the windows. Smooth window shapes. Okay. So if I wanted, for example, say minus 60 dB attenuation, I would probably go with that Hamming window there, or Hanning, or just try some of those to see what happens. Or I could actually also use so-called Kaiser window. Anyways, the system goes exactly the same. So smooth window shape. For example, we calculate WW equals, let's see, Hamming. And then Hamming requires just one parameter, which is the length of the window, L-point symmetric Hamming window in the column vector, Hamming length of NN. There. Same length as indexes. There. This is column vector, but our system parameters are row vectors. So basically, at some point, now we are basically multiplying this original box window with Hamming window. So fundamentally, it's the same thing as using this kind of multiplier window for the sink. And now our HHWW would be HH original one times dot times WW transposed. Okay, that prime there means that when we have this window, actually it returns, the window function returns a column vector. We need to transpose it the same way as our the system parameters. That's why we need the prime there. So this is the a smooth sink. And the frequency response of this one would be, well, we started with the this is the original, so 11 point sink. Okay, we started with this one. Good. And now I will just show the frequency response of this new smoothed wind sink. Okay, what happened? A lot. We still have the minus 3 dB point here. Don't worry about the scaling here. It's really doesn't, at the end it doesn't matter since we know how to scale it. So it's still at 100 dB, but then the stop and attenuation is now somewhat at much better level. We can see it better with the higher order number. So HH, oh, actually, oops, sorry. Window shape first. We have this 111 points. Wide HHWW. I make it 1. There, smoothed sink for this one, and frequency response CW1 there. Okay. So we started from that sink multiplied with the smoother window, and now we have a system FIR filter with minus 60 dB on the stop band, means 60 dB attenuation on stop band. Okay. And with the desired cutoff frequency. Now the question is the transition bandwidth proper? If we could tolerate, say, double of that transition bandwidth, so this transition bandwidth, if I see it correctly, let's zoom it a little bit to see it better. So our cutoff frequency is, let's see, data cursor where I have the, okay. I'll just add something here. Where are the toolbars? Tools, not data, but I can't do it. I'll add a couple of lines here just for fun. One line at 100 Hertz, that's our cutoff frequency, so line 100, magnitude is minus 82, 0, something like that. Let's see. Oops, minus 80. There, that blue line is now our cutoff frequency, and based on this data, I would say our let's see. Our stop and start frequency would be at okay, somewhere there. Let's see. XX, YY. One graphical input from this point. Click. Whoa. So 130 Hertz stop band start frequency. Okay. So if that means that our stop band or the transition bandwidth is now 60 Hertz. Oh, no, 60. 30 Hertz. Okay. Sorry. Oops. Transition bandwidth 30 Hertz. FC minus FSP, basically. 30 Hertz. And if that's, too much, so if we could tolerate with, say, a wider transition bandwidth, let's see what happens. For example, say 50 Hertz. It's simple scaling. Now our length of the filter, NN1, is 111 points. We just multiply this one with the new the current transition bandwidth divided by required transition bandwidth. That's our new length. So we have 66.6. No, that's not intentional. 66.6 values. 67 values. Right. So need 67 values on impulse response, which is simply this one. NN2 equals from minus 33 to plus 33. Right. 67 values on that index. And now we can do the calculations for that one. Not NN, HH1. Okay. Oh, not that one, but this one. That's the sink. Then the window. And now we have the length correctly. Whoa, what happened? Oh, I didn't do the HSWW. Okay. So that's the windowed sink. Smoothed sink. And now we can do the frequency response. There we go. And again, seeing is believing. So if I go and just magnify that one. Okay, now our our cutoff frequency is at 100 Hertz still, but now at around that 150 Hertz we have the stop and start frequency. Okay. So we can control the cutoff frequency by sink, that's Fc over Fn term. The transition, stop and attenuation we can basically control by selecting the proper window shape, and then the transition bandwidth, so how fast the frequency response actually drops down to from the pass band to stop band. We can adjust that by doing the width of that system, width of the filter. Okay. Then that's basically everything about low pass filter. Now how to transfer that filter property to pass band filter. So low pass to band pass filter. Pass filter transformation. And there we just need to modulate it. Example. Modulation of this one to, say, center frequency of, all right, what would work? 400 Hertz. That looks good. It's up to 400 Hertz here. Well, that's Nyquist frequency somewhere there. So I would transfer this filter property so that, let's see, line to center frequency 400 Hertz. Okay, on that point in here. So basically what I'm expecting to get is I'll get on the right hand side I will get exactly like that curve, and on left hand side I will get actually the mirror image. And now we have 100 Hertz bandwidth for that low pass filter. I'm expecting to get 200 Hertz bandwidth for this band pass filter. And also what I'm expecting to get, since we are splitting the spectrum to, on positive and negative sides, that the amplitude goes down by 2. So we have to compensate that one. Okay. So modulate with center frequency. So FM equals now that 400 Hertz. That's the center frequency. Center of band pass filter. Whoops, filter. And for example, we can take that HH2, which was quite nice, that one, and modulate that one. So we have HHWW modulated 2 equals HHWW2 dot times cosine of 2 times pi times FM times sample points divided by sample rate. Right. So sample times are actually those indexes divided by sample rate and multiplied by 2. Maybe I should put it here. That scaling of 2, well, that's because we are splitting the energy of that filter into 2 parts. Scaling and modulating. Yep, sorry, NN2. There we go. And let's see how close I actually got it. HHWWMM2. Yeehaw. Oops. Oops. Color. That red line there is now the center frequency at 400 Hz, so that's the modulating frequency. I multiplied it 2, so the filter is still a unity gain. And yes, the bandwidth is actually double of the cutoff frequency of the original low-pass filter. But the stop band attenuation stays rather the same as it was for the low-pass filter. For low-pass filter, it was 60 dB, and so this also has roughly the same stop band attenuation. Some modification has been done here, but nothing big to worry about. Okay. So that was from low pass to band pass. Then from low pass to high pass. Same thing, but we modulated with cosine of NP, which is actually same as -1 to power of M. So low pass to high pass. HHWW high pass 2 would be just HHWW 2 dot times -1 to power of 2 not NN2 there. So -1 to the power of NN2 means it takes that -1 and puts that into exponent of either even or odd term, and then you will get actually same effect as with cosine n pi. Both are equal the same, or HSW2 times cosine NN2 times pi. That will do exactly the same thing, except -1 to the power of so for example 1000 would be exactly 1, but if you take cosine of 1000 times pi, it's not necessarily 1 due to the calculation accuracy. Okay. And again, seeing high pass, there we go. We started from low pass filter and modulated basically as a high pass filter. And this one basically has exactly the same bandwidth as the low pass filter. Now the question is just, if I had for example, if my design required a cut-off frequency, for example, for 400 Hertz for that high-pass filter, then I would need a filter, let's see, I would need to filter with that green bandwidth, so 600 Hertz bandwidth. So now you just need to be careful with these transformations about that you will get the correct frequencies for cutoff frequencies. Everything comes from the bandwidth. That's the design factor for this low-pass filter. Okay, but otherwise, always the same design flow. First, select a window shape to smooth it. Then you have the sink for the cutoff frequency. And then you start with a window length and adjust this window length so that you will get correct transition bandwidth. Okay, and then finally you will modulate. Maybe I should do this high-pass filter again, just for fun. And I'll start with HH2, I'll make it HH22 and not FC, but there I have 600 Hertz cutoff frequency, the bandwidth. Okay. Then I will calculate the HHWW. All right, that one is 22. Smaller sink. The sink is still the same. No, the sink is different, but the window is still the same. Okay. And here that one would be different. Okay. And this one would be something like that. Oops. So now we have the required bandwidth there. Okay. And now basically the last part would be the from how about that band pass filter? Band stop. Band pass you will do with the modulation, band stop you do with the addition. And adding FIR filters is extremely difficult since you have to add those parameters. Okay, so HH for band stop equals HHWW2. Okay, was it 2? Oh, no, it was just HHWW. Which one was the low pass filter? Maybe that one. Okay, I'll check. I'll check it. Frequency response of HHWW2 1024 FS. So we have this filter. Yeah, that's a low pass filter. And then we have this high pass filter with this funny 400 Hertz cutoff frequency. And if you add these together, WW band stop equals WW HH2 plus WW HH high pass 22. No, HS. This way around. Better. And the frequency response of this filter there. So it actually combines the filter properties, and yes, the stop band attenuation gets lower. So previously we had 60 dB stop band attenuation. This goes to something like 50 some dB because we are adding terms. So we are adding fundamentally the outputs of two filters with phase. Okay. But anyways, now we have the from stop band basically starting at 150 hertz up to 350 hertz. That's the stop band. This lower cutoff frequency 100 hertz and upper cutoff frequency 400 hertz. Okay, good. Let me take a quick look on the exercise of today. Do I find there is no voice level and voice requirements? Okay. The rest, basically the first half of this exercise is about making a filter by these requirements what I tell you. The second part is making those filtering requirements yourself. Okay, you need to, there is a noisy voice sample on that link what I give you. Download that one, and basically what you have to do, first you do the spectral analysis. So there's a noise with voice or voice with noise. Do the spectrum analysis of the signal. Spectrum would look like, well, something like that. It might be some, I think it looks more or less like this. I don't remember if I actually added a nasty voice peak here, maybe not. Fundamentally, it has the signal part, and then it has the noise part. Maybe that one, I don't remember exactly. How you recognize what part is voice and what part is noise? Signal spectrum doesn't show it. What you need to do is you need to do the spectrogram. Time, frequency. Since if you have this noise, it shows as just, noise in spectrum. If you have voice, it has some, some definite areas here. And well, if you have, you could also either use some Google, or then if you have microphone, you can basically record your own voice to check where is your signal in the spectrum. Right. If there is a, you have also some chirp signals or a single tone signals, they will end up showing like that in the picture. So if that is some human speaking, then you would be interested only on this section here, not that one, which gives you parameters like what is the stop band attenuation on the single spectrum. You need to lower this noise at least to the signal level. Even more is better. So you need to basically break that one and get this noise lower than the signal power in dB. That gives you attenuation. Then you must have enough of attenuation here, which means that the stop band start frequency. Okay, then you have the signal I think this is not there. I really hope that it's not there. I need to check. Then that signal itself, you don't want to mess up with the signal too much, meaning that you need to set up the cutoff frequency for the system so that this part goes through the system as well as it can. So you don't want to mess up with that one. So fundamentally, you now have all the required information to design the filter. You have, for filter design, you have cutoff frequency, stop and start frequency, and attenuation. Cutoff frequency you use for sync. Stop and attenuation you will do use for selecting the window shape. And this transition bandwidth depends on the width of the filter. Okay. My work here is done. Now it's your turn to continue exercise. You can stop the recording. Thank you.